Swayam Prabha. Digital India. Educated India.
Good afternoon. Welcome you all to this next lecture in this course on analytical, spectral and microscopy applications of inorganic compounds and nanomaterials. We have been going through in the past few lectures on the X-ray diffraction in specific context to the powder X-ray diffraction. So within these classes we have already looked at the basic principles, how to index the things, and then lately we have been looking at of course how to get the lattice parameters and the refinement, and then followed by the applications of it. So in the previous class towards the end I showed you the variation in the powder diffraction that you find for example a chitin which is isolated from different sources, and similarly chitosan which is from different sources of that. And of course again in the chitin you have alpha and beta types, and both of these that we have looked at. The reason why we have looked at this their powder XRD is these are used as a matrix material for making the composites. Let us look at some more composite XRD in terms of characterization, understanding the thing. So here is an example, draw your attention to this particular slide, is a phase identification in copper oxide, zinc oxide composite. So you have the, there's no need to read this, you can go through that later on. So if you look at the copper oxide powder XRD, you can see that these are the ones, and these will match with the source that you have in the online data. This is the zinc oxide which will match with the corresponding zinc, and this zinc oxide is the hexagonal form and the copper oxide is the monoclinic form of that. Now these two are taken and make the composite to that. So you can see that copper oxide with zinc oxide. So this is for copper oxide, this is for the zinc oxide, and this is for the mixture. So you can see the peaks coming from the copper as well as from the zinc part of it, but with different ratios of intensities, but with different width of the peaks, etc., etc. And this is where you can identify the both the components present in that. We look at this which is calcined to that, and when you calcine you get a peaks without much of the background things, and all the small peaks also become much better when you calcine the things. That means you have some other materials which may be present, either moisture or other kinds of things which are present. When you calcine, they all go away, so you get a much more cleanup. And now in this, if you look at the individual assignment, and you know the assignments for the copper oxide, for example here this is for the copper oxide, these are the planes, etc., and these are for the zinc oxide. Now if you try to identify the corresponding ones, you can see the ones which are coming from the copper oxide, the ones which are coming from the zinc oxide. So their phases of the monoclinic and the hexagonal are still retained even after a composite is being formed, and now the composite is used for some application of that. So that is how the XRD can help identifying what is there in the composite basically. How is it, in what form these individual components are present, therefore what one can expect out of those things. Okay, now let us look at another example of composite. This example of composite again is from the graphene oxide with the tungsten disulfide, so WS2. And if you look at this graphene oxide, the graphene is all very well known, understood, and then you can see this WS2. So the WS2 shows a diffraction pattern at these mainly 1, 2, 3 and 4 major peaks, 002, 004, 006, 008. Okay, and so that shows that there is no other contaminant peaks were detected in the pattern. So now if you take a mixture of the WS2 and the graphene in one ratio of the composite, in a different ratio of the composite, you can see things over there. So what one is labeled as WSG1 and WSG2. So you can identify the graphene related peak also, that G is being labeled as that. So you have a composite formed between the graphene and the WS2. So you can see the main 002, 4, 006, 008 peaks as well, and the peak coming from the graphene part of it, all of these. So you can fully characterize the composite for these kind of the features of this, and this shows there is no other impurity got into this one. So both the graphene and WS2 related diffraction peaks were located in the composite samples, which proves the formation of heterostructure between graphene and WS2. So moreover, the diffraction peaks are sharp with high intense and slightly shifted to the lower angle side in these things. So this is because the graphene, when you mix or when you make a composite of WS2 with a graphene, and there is certain level of graphene influence, and that enhances the crystallinity of that. So crystallinity will make what? A line bit sharper. Okay, and crystallinity may also change because the crystal size, shapes, etc. will change. There could be a shift in the not necessarily low, but here is a shift. Presence of graphene enhances the crystalline nature. So the average crystallite size was estimated from the Debye-Scherrer equation to be, if you take the simple WS2, it's 32 nanometer, and if you go for one of these combination 39, other combination is 47, which is in line with the changes that you observe in these things. Okay, so therefore based on the crystallite sizes, you can say that the crystallites are changed in this. Whatever the crystallites, whatever the particles that you have, the particle sizes, they differ, and therefore because of the influence of the graphene on the WS2, these changes have come. So that is what you can call a composite is formed. I hope that is understood. Look at one another example of the graphene oxide, but this time this graphene oxide which has got different layers joined together, and that you try to put into different kinds of rubber materials. So one of them is the rubber material which is hypalon, which is called chlorosulfonated polyethylene. Another rubber is polychloroprene rubber. There are a few more which are there in this paragraph. If you just go through that, you will be able to find then chlorosulfonated polyethylene kind of a rubber, and hydrogenated carboxylated nitrile butadiene rubber. Okay, so in all these things you can introduce this graphene oxide which has got the layers of that. So but when you put that and look at the powder diffraction, you don't see the graphene oxide peaks corresponding to that, either in this particular hypalon, the rubber composite, or this is the one which is the polychloroprene rubber, which is again the composite, and there's the other one where the diffractogram is not shown. In another case, hydrogenated carboxylated nitrile butadiene. So in all these cases, the graphene is basically exfoliated in the composite. So outside they are okay, but this graphene oxide, basically the graphene oxide is more exfoliated, so therefore we don't find that peaks corresponding to that. So there are other kinds of rubbers also they have tried. Bromobutyl rubber based on nano composite reinforced with ionic liquid modified GO. Okay, so in all these cases, the graphene oxide which is gone into the composite, which is there embedded into the composite, but will not be seen in the powder diffraction because its characteristics are changed by exfoliation. Okay, along with the microstructure intercalated and exfoliated, it's gone into the composite, and then it is also exfoliated. Intercalated because the rubber, the polymer, the fibrils, so into that this can go. Of the graphene or rubber nanocomposite, the degrees of crystallinity of the nanocomposites, which indeed plays a major role in governing the physical and mechanical features of this. Okay, so if you put some other component, you can have electrical features too. So use this rubber as one component and your material the other one, in this case graphene oxide, but you can put many other materials and make such kind of a composites whose properties you are trying to look for to change. For here, in this case, the physical and mechanical properties of the rubber changing in that. In the other cases, it could be the matrix. In case of rubber, it could be a matrix. In case of graphene oxide, you can have any other material, and therefore you can change the light properties, electrical properties, magnetic properties, many of these things in the composites of this. Okay, so we have looked at quite a few examples of this. I just came across one publication very recently in the ACS Nano 2019. This paper is basically published with the following information. No doubt that X-ray diffraction can be used very well for characterizing the material, nanomaterials. So using the XRD, you can get information which is complementary to microscopy, to spectroscopy, and you can find the phase identification. You can find the purity or any impurities there. What is that impurity? How much is that impurity? Crystallite sizes, polycrystallinity, other things, and single crystallinity, amorphous nature, structure, and some cases even morphology. So many things. So powder X-ray diffraction can help in getting all these different kinds of characteristics of the powder or a solid material of that. But it is not that the information all the time that you get and the interpretations that you make, they need not be very much in line, because of the major pitfall in that is in the powder sample is that you have different particles. Each particle may have a domain, crystalline domains. Okay, very rarely it could be a fully single crystal, but most often there could be crystalline domains. Those crystalline domain from one particle to the other particle, or from one crystallite to other crystallite, need not be the same, they can change. So, and that means also these crystallites, whatever the crystalline domain, may have different size of the nanoparticles, different shapes of the nanoparticles. All of these are possible. So nanostructures, not nanoparticle, nanostructures. So therefore, the information that you interpret out of the powder XRD, one has to be very cautious. Has one taken care of the variation in this the nanoparticles, whether these domains, the crystallinity domains, are same or different? Or when you are looking at the size of the crystal, whether it is the same as what you got from the TEM. So one can check by transmission electron microscopy the size of the things, and to some extent even the shape of the particles, etc. you can get. So you can use that information and see to fit with this and try to see the explanations that can be made. Okay, so as a bulk technique, the information it provides can be correlated with the microscopy data to test the microscopic observations on a smaller number of particles represented in the majority of the sample or not. So because in the TEM, obviously you are looking at each of the particle separately. In the powder, you are looking at the particles of various oriented in various directions, and then each particle may have a different domains. So crystallinity domains, crystalline domains, on those things. So therefore, one can be wrong in making the interpretations of that, because in the absence of such information, the interpretations could be wrong. Okay, so nanoscale material with an emphasis on inorganic nanomaterials of various size, shape, dimensionalities. So that is why this paper has been brought to the students, researchers, various people who should exercise caution while explaining the powder XRD. So some features you may explain to something else, but maybe different. For example, the width, always not necessarily the size of the particle, but it can also be the instrumental parameters, and many other kinds of parameters are also possible. Okay, so they also say in the end, it is important to recognize the capabilities and limitations of powder XRD for nanoscale materials because of the size, shape, polycrystallinity, and the crystalline domains change between one particle to the other particle when collecting and analyzing the data, as well as to ensure that the claims based on XRD data are accurate, appropriate, and not overreaching. That means a wrong interpretation or over interpretation, both of these are there. So what are the points that let us take up a few points in this from this particular paper where one can go wrong, and that's what they showed. Now here is a case, you don't need to go through all this. This is for cadmium sulfide. Why they took up the cadmium sulfide was it's one of the important material, which is a quantum dot material, which people have been using a lot in nanoscience and nanotechnology. Now this is very important nanoparticle because it's a band gap, and then its color, its electronic, its optical properties. These are all dependent on the shape of this quantum dot or cadmium sulfide particle, as well as the size of that. All of these things are important. So the size and shape of these are important. So otherwise it will be, interpretation will be wrong. Now we will look at how that is understood now. For example, woodsite is the most common form of the CDS, cadmium sulfide. Okay, so if you look at the structure, you can see it's a lattice structure or unit cell structure, the sulfurs and the cadmiums being in that. So you can see the layers of the 100, 002 and 101, variety of these things you can see. And there are many other higher order reflections are also there. You can see that they're very nice. And this is from a bulk. This is from a bulk kind of a material and very nice. Cadmium sulfide, all the planes, not only the planes of these planes you can see. So all these can be labeled, everything is known very well. So, but when you try to reduce the crystalline size or the crystallite size, along with the particle, of course, size decreases from bulk to nanoscale dimensions, the XRD becomes broadened. Most often, the broadening can also happen from other reasons as well. Each peak can be evaluated independently, okay, each of that, because you have a peak, therefore you can evaluate the crystalline domain in that by looking at the breadth of that peak, etc., and the profile of the XRD profile. Using the XRD profile, width and intensities, etc., you can look at the crystalline domain size. So as long as the sample is more or less uniform and spherical particle, this will match with what you see even in the TEM. But otherwise it will not be. If they are not uniform, each particle do not have exactly the same the nanoscale crystalline domains. The crystallinity domains are important. So people can go wrong. They use instead of degree, instead of radian, they use using the degrees, and also crystalline sizes, etc. All of those they presume that they are all same size, they presume that they are all same shape, etc. So all of these aspects will make the interpretations can go wrong. So now you have seen the full the bulk one. Now see, if the crystalline domains are all same, this will exactly fit with the what you have from the TM, whatever the part. But on the other hand, the same cadmium sulfide now, which was bulk in the previous slide, and it is not the bulk, it is the nanoparticle with the different sizes. The sizes going from a micron to a nanometer of 50, 25, etc., etc. So even if you see the micron is reasonably well resolved with sharp kind of a peaks that you would see here. Now when you bring down to the 50, you can see there is a reasonable amount of broadening and much more by the time you go from 50 to 25. And when you go to something like 10 and 5, more or less you cannot much see. You see that? Almost completely broadened kind of things. Okay? So this is very important to look at the size functionality changing, but the breadth of the peaks can also happen from instrumental parameters as well. So one needs to try to look at, compare whether your powder has got the same or different by using the TM. So you use the TM, and TM will tell you what there, if you do a quantification of that, you can tell what the fraction of the particles are of this size, what fraction of the particles are of the other size, where you can get the particle distribution, size distributions. So then if you use that parameter and try to refine, then your parameters will go better, and then your interpretations will have a minimal errors kind of thing. So particularly when you go to 5 nanometers and below, then you have completely, so size dependent XRD peak broadening has important implications for nanomaterial characterization. For example, if TEM analysis shows spherical particles having an average of 10 nanometers, but the XRD has sharp peaks, more consistent with the particles having much larger crystallite domain, and you can go and check from this the formula, you can get the, for each of the peak in the XRD you can get the width or the size of that. So from the width you can get the size. The majority of the bulk sample is not composed of the 10 nanometer particle. So in your powder it is not. Okay, so therefore you are using that powder as a bulk as opposed to the what you have in the TEM, and that is how you need to make a comparison between the microscopy and this powder X-ray diffraction to make that. So we have looked at how a size variation. Now let us look at how a shape variation. Okay, these cadmium sulfide, these particles, okay, or quantum dots, dot when it is circle, but there can be nanoparticle when it is other shapes. You can say the shape is of this kind, the shape of this rectangle type, the shape of rod type, and there are many shapes are possible. These are the major kind of shapes that are taken. Now if you look at each of these, their spectral things, this is in the bulk without much of this, and then you have 25% of this, 50% of this, and 75% of this, almost 90% of this. If you have all of it or 99%, you get only 2 peaks of this, and the 2 plus 2, 3 small peaks when you have 75%, when you have 50%. So therefore the amount of this would reflect in the kinds of the peaks. So one needs to know what are the peaks corresponding to this kind of a shape, then pick up those and then analyze. Similarly, if you take a rectangular kind of a peaks here, particles, now you can see the rectangular particles bulk all 25%, 50%, but this is at 100,200, this is 002, 004. So using the reflections of 002, 004, you can estimate the this kind of a shape of things. Of course, you can also look at the width, other parameters. By looking at 100,200, you can look at the composition of this. So that is way how you can break up your powder XRD into various these things. Then you need to refine separately using this some amount, this some amount, this some amount, then club all of them, then you will get a better refine. If they are cylindrical kind of things, so only one, that is 110 get remain when you have a large number. Okay, so you can see with 25%, 50%, 75%, 99%. So therefore you have standardized, these are all standardized one. You can use in your sample, you can identify how much of such kind of things are there, how much of such kind of things are there, how much of such kind of things are there, and you can also look at their peak widths, etc., and then compare. Now if you analyze this and by making a comparison with TM, now use these parameters into your powder XRD refinement, then you will get a good interpretations of your compound, and that's what is basically explained here. Okay, so we have we are more or less coming towards the end of this particular the topic on this powder XRD, in specific X-ray diffraction in general. I've shown you at one stage that S value can be measured, can be calculated by using the sine square theta values, etc., and that is where you can see for this how do they match with what kind of the reflections. Okay, so that is what kind of indices also. So if you have a simple lattice, this kind, we've shown you earlier also, under the cubic, face centered. So some of them only are there. That means other peaks are absent. All other peaks where there is no value shown here, they are all absent. And only these are. So in the simple or the primitive lattice, you have the maximum, and this is the total S value. That is h square plus k square plus L square. Then face centered, then body centered, then the diamond. Therefore, you can easily make out, and further extended for S values 30, 31, 32, etc. up to 49. So you can all make, and even beyond. So using that h square plus k square plus L square and converting into their Miller indices planes, the planes with the Miller indices, there one can identify the kind of a lattice that we have. I already shown you there, and these are kind of a data which is available directly. And most of the times if you feed your data to the computer which is having all this, that will work out and give you as well. So we have gone through a range of informations in this particular topic, starting from what is a diffraction, which this species will make the diffraction atom, scattering strength, their presence in plane, and the plane's diffraction, scattering, interfering, and then making the diffraction, where you have intense or no intense, all those kinds, or medium intense, less intense, all of these kinds of things, everything. Then using this particular from the data, how a powder diffractogram will look like, how it emerges, and how it is being digitized in the form of the diffractogram. So we have looked at that, and what does it store basically finally, and how do you interpret this? These intensities and the theta values should be converted into D, into sine theta's values, and the HKLs, and to the lattice parameters, all of those, their refinement. And so then using just simple combination of these powder diffractions, you can get a diffraction of a mixture, and you can identify the mixture, you can quantify that mixture as well, and various examples. So composites are all like that. Why you're making composites? Because you want to get some new parameters, new properties out of them, and that's where for that you need to characterize, and that's what you're doing using the powder XRD. Okay, last but not the least, in all the cases I've always brought, there's some kind of an exercise you require so that your understanding becomes better. So here I brought something. As I said, all the data is available in the PXRD, and that is accessible. You can go access anything. For example, coordination complexes. A large number of crystal structures are known. Powder XRD data is known. No problem. Absolutely. And what I have brought to your notice here is some information which, if you use it, you can take a selective one and then focus on that. For example, powder XRD data is available in the PDF for each and every compound that is being studied and reported. You are advised to take 3 different inorganic or coordination compounds, wherein the metal varies from 3D to 4D, 5D. Let the ligands, let the counter ions be same, but the ligands oxidation states are same. Then pick up that powder XRD data for these 3 compounds and practice. What are you going to practice? Labeling, indexing, assigning the planes, identifying the lattice type, deriving the unit cell parameter, and then cross-check all these with the published data. And preferably you take the cubic type, because that becomes easier. So this will give enough practice. So there is no need to give a questions like this. There are millions of data is available. Another one, this is for the coordination compound. Another aspect I would expect you to do is that pick up PXRD pattern or data for gold or silver nanoparticle, whatever you like, of different sizes, and compare and discuss the data among these. So you pick up the data, powder XRD data for different sizes, either this gold or silver or both, or even a combined one, it doesn't matter. You can look at that. Derive their particle size from the powder XRD in each case from each of the size case. Then compare the same with the known size data from the TM. So for the same powders, for the same polycrystalline material, if the TM is available, it will be very good. That means when you are choosing, you choose those data sets where the TM data is also available. Then what you do is, so what is TM is showing? what is your powder XRD showing? Powder XRD is the size of the particles that you derived. Now from this you can make out whether the diffraction data can be straight away interpreted or need some modifications like earlier to fragment using the shape, size kind of information and then interpret. So therefore you can draw your appropriate inferences based on this also. Okay, so I think that takes care of all the aspects that are required for this particular course in terms of the powder XRD applications to inorganic materials and inorganic compounds and nanomaterials. Thank you very much.